So water truly is an extraordinary substance. We take it for granted. You know, we use it all the time. We drink it, we bathe in it, we play in it, we water our lawns with it, we do all kinds of stuff with it. But it's a really, really unusual chemical. It's the most common and the most important liquid on Earth. I mean, think of other liquids. What other liquids do you encounter? Alcohol. Do you run into pure alcohol very often? No, it's usually mixed with water. Mercury is a liquid. You see it in thermometers sometimes.
Oil.
Oil is a liquid. Things like gasoline, right? But what is there by far the most of? Water. The oceans, you know, just huge quantities of water. And the other liquids that we do encounter are much smaller. One of the weird things about water is even though it has a low molar mass, it is a liquid at room temperature and not a gas. And that is due to hydrogen bonding. Water is the main solvent both in our environment and in living organisms. It has a crazy high specific heat capacity, 4.184 joules per gram degree Celsius. That is much, much higher than most substances. And as a result of this, it moderates our climate. It helps to reduce the large fluctuations in temperature. And then the other weird thing about it is it expands on freezing. Most substances, when they go from a liquid to a solid, they become more dense and their volume decreases. Water doesn't do that. So here's a table. We've seen one similar to this before, but this one has a little more detail in it. Here we have a graph of boiling point versus period in the periodic table. And these are compounds of elements with hydrogen. So the blue is group 6, the yellow is group 5, the green is group 7, and the red is group 4. So group 4 follows this really nice little trend here. It makes a fairly straight line. As you increase the size of that central atom, carbon to silicon to germanium to tin, we see that the boiling point of the substance increases. Why does it do that?
Oh,
Those things.
I look back at nature.
Nature has something to do with intermolecular forces.
Dispersion.
Dispersion forces. So those instantaneous dipoles that induce a dipole in the next one, and then you got this little bit of attraction, those get stronger with larger molecules because the large molecules are all floppy and they get lopsided more easily, right? So that's why we see this trend here. Well, if we disregard period 2, the period 3 things generally follow that same pattern, right? But period 2 for nitrogen, fluorine, and oxygen are completely bucking the trend, aren't they? Why? Why do these do that? Hydrogen bonds. In order for their boiling points to be so high, that means that their intermolecular forces are much higher than these guys. And it's not the dispersion forces. And it's not even the dipole-dipole forces. Because things like phosphorus trihydride, selenium dihydrogen selenide, I guess you'd call that. These guys are polar as well. They have dipole-dipole forces. But these 3 have hydrogen bonding. Remember, ET phone home, F-O-N with hydrogen. Here we have oxygen with hydrogen. My pointer, where's my pointer? Oxygen with hydrogen, fluorine with hydrogen, nitrogen with hydrogen. But oxygen here is the craziest of all of them. Book has an interesting little section on water pollution. I'm not going to go into it in great detail, but obviously it's important to have clean water. We can't survive without clean water. There's 2 basic types of water pollution, chemical and biological. Biological pollutants can generally be destroyed by boiling or perhaps chlorinating the water. Chemical contaminants, you can't do that. If you boil it, sometimes you make it more dangerous because you concentrate the pollutant. So it's important to be aware of water pollution and do what we can to avoid it.